ID the Future, a podcast about evolution and intelligent design.
Greetings and welcome to ID the Future. I'm Andrew McDiarmid, your host. I'm sitting down today with Dr. Jonathan McLatchie, fellow and resident biologist at the Discovery Institute's Center for Science and Culture. Previously, Jonathan was an assistant professor at Sadler College in Boston, where he lectured biology for 4 years. He holds a bachelor's degree in forensic biology, a master's degree in evolutionary biology, a second master's degree in medical and molecular bioscience, and a PhD in evolutionary biology. His research interests include the scientific evidence of design in nature, arguments for the existence of God, and New Testament scholarship. Jonathan is also founder and director of talkaboutdoubts.com. Jonathan, welcome to the podcast.
Great to be here. Thanks so much for having me on again.
Absolutely. You know, the first thing I should note is that Jonathan hails from Bonnie, Scotland, which is also my homeland, in case you haven't noticed, listeners. So I think this might be the first time that two Scotsmen have graced the microphones on ID the Future.
It only takes one.
It does only take one, yeah. But here we have two, and I don't think it'll be the last time. So, Jonathan has recently posted a series of 3 articles at evolutionnews.org about the blood clotting cascade and why it poses a challenge for Darwinism. He also responds to proposals put forth by the late biochemist Dr. Russel Doolittle that attempt to explain this amazing system through evolutionary pathways. So Jonathan, in your first article in this series, you call the blood clotting cascade an incredible, tightly regulated, multi-component cascade that intuitively points to intelligent design, unquote. And it's true. The more one learns about this amazing process, the harder it is to credit an undirected process for its origin. Let's start with why you wrote this series.
Yeah, so Michael Behe's been doing a series of videos for the Discovery Science YouTube channel. It's called Secrets in the Cell, and listeners might be familiar with that series. Highly recommend it if you haven't had a chance to listen or view those videos yet. They're truly excellent. Anyway, he did a video as part of that series on the design of the vertebrate blood clotting system, which also happened to be one of the examples of irreducible complexity that Behe adduced in his first book, Darwin's Black Box, back in 1996. Anyway, this video that Behe did for the Secrets in the Cell series was posted on the Stephen C. Meyer Facebook page, and one of our critics posted a comment saying, oops, and linked to an article by the late Russel Doolittle, who was a very prolific biochemist who died sadly in 2019. And Doolittle's paper attempts to give a step-by-step evolutionary account of the origins of the vertebrate blood clotting system. And I read the paper through, and I also discovered that Doolittle had published a book on the subject of the evolution of the vertebrate blood clotting system. And so, of course, I was interested to see what Doolittle had to say in the book as well. So I purchased the book and read the entire book. And I was left wanting as far as an adequate account of the origins and evolution of the vertebrate blood clotting cascade, as we'll discuss in due course.
Okay. I like the way you put that. You were left wanting. Well, some of our listeners may be familiar with this cascade, this system, but others may not. Can you define what the blood clotting cascade is and what it does?
Absolutely. So the blood clotting cascade is essentially the mechanism by which the body stops you from bleeding out if you have an injury, an insult to your tissue, or tissue damage. And essentially, if there was no means of clotting the blood, then a tiny injury would result in all of your blood leaving your body, which obviously would be a problem. And so the blood clotting cascade, it's also called coagulation. So if you hear me use the term coagulation, I mean the same thing, is essentially this physiological process that helps to maintain the integrity of the circulatory system. And so it essentially involves a series of intricate molecular and cellular interactions that result in the formation of a clot at the site of injury within a blood vessel. And this prevents excessive bleeding and promotes the healing of wounds.
Okay. Now, I understand there's something called a platelet plug that forms, and that's part of this clotting system. Can you tell us a little bit of that?
Sure. So the first heroes of the blood clotting system are the platelets, which essentially adhere to the exposed collagen fibers in the damaged area, and they undergo a conformational change, and they release various substances that are stored within their granules, which promote further platelet activation, and they attract more platelets to the site of injury, and that forms a plug over the hole. And these activated platelets, they bind together, and that forms clumps or aggregates, and that reinforces this platelet plug. And this is only essentially a temporary seal, so it's a quick fix sort of situation. It's not supposed to be a long-term solution because it's not sufficiently strong to hold for long. And so as the blood continues to flow through the injured vessel, it can dislodge the platelets. And so the formation of this platelet plug, which essentially initiates what we call the coagulation cascade or the blood clotting cascade.
Okay. And the cascade itself, how is it controlled? I when I was looking at this, I was reading all about this factor informs this factor, and then this factor gets turned on. It's quite intricate.
It is. It's incredible. Yeah, I've long been fascinated by biochemistry, molecular machines, and the vertebrate blood clotting system is just, it's at a level of its own. It's just absolutely incredible. I was teaching a class this past year at the college where I used to teach in anatomy and physiology, and I had the opportunity to lecture on the vertebrate blood clotting system, and was just very struck at just the engineering prowess and design of this system. It is a very complex system, and there's a lot of technical detail, and so I'm not going to get into the weeds in excruciating detail in an Idea the Future podcast. However, so I'm going to give a flyover overview, but if listeners would like to get into the weeds a little bit more, then they're welcome, of course, to go and check out my 3-part series at evolutionnews.org, where I give a lot of technical detail and a lot more fleshing out of this process and the arguments that we're going to be discussing and reviewing here. But just in brief, so I like to, when explaining the blood clotting cascade, I like to start with the culmination of the vertebrate blood clotting cascade and work backwards, right? So the ultimate objective of the vertebrate blood clotting cascade is the formation of the fibrin gel that reinforces the initial platelet plug. And that strengthens the clot. So the clot is made of fibers that are composed of a protein called fibrin, which circulates in an inactive form that's called fibrinogen in the blood plasma. So fibrinogen, in order to be converted into fibrin, it has to be cut at particular sites, and that is accomplished by another protein called thrombin. And so thrombin cuts fibrinogen to form fibrin, and the fibrin proteins will then form the platelet plug. Now, if you only had fibrinogen and thrombin, then what would that mean? Well, thrombin would constantly cleave fibrinogen, and the consequence would be uncontrolled and excessive clotting, right? Where you're constantly converting fibrinogen into fibrin, and that would be a problem because you'd have excessive clotting throughout the bloodstream, which of course you want to avoid. And so to avoid this, you have to have a mechanism for regulating the formation of fibrin from fibrinogen. And so blood clotting involves the use of what we call proenzymes, which are essentially enzymes that are retained in an inactive state, and they need to be converted into active enzymes through specific cleavage by proteases such as thrombin, right? So thrombin itself exists in an inactive form, which we call, you guessed it, prothrombin, right? And so to convert prothrombin into active thrombin, you need another enzyme, which is called factor 10A. So when we put the A after the name of the factor, then that designates the activated form of that particular factor. Along with its cofactor, which is factor 5A, which assembles on the surface of platelets or other phospholipid membranes to form the prothrombinase complex. And that complex provides the platform for the subsequent activation of prothrombin. Okay, so factor 10A also exists in an inactive form, factor 10. And factor 10 may be activated by two different pathways, the extrinsic and the intrinsic pathway, right? So far we've looked at fibrinogen, thrombin, factor 10, and factor 5. And Behe in Darwin's Black Box contended that this, which is called the common pathway, which is after the fork, as it were. So there's two different pathways called the intrinsic and the extrinsic pathway that can lead to the activation of factor 10. And so the intrinsic and extrinsic pathways converge into what we call the common pathway. And these four proteins I just listed, so we've got fibrinogen, thrombin, factor 10, and factor 5, are the protein components that Behe argued in Darwin's black box to comprise the irreducible complex core of the system. And of course, you also need a mechanism for activating factor 10 in response to tissue damage. And so at minimum, being highly conservative here, our irreducible complex system is going to be composed of at least 5 parts, right? So you need fibrinogen, thrombin, factor 10, factor 5, and some mechanism of activating factor 10 in response to tissue damage. So the extrinsic pathway, so what is the difference between the extrinsic and the intrinsic pathway? So in the extrinsic pathway, which is so named because it's triggered by the external tissue factor, which is also known as factor 3, gets released. And tissue factor forms a complex with factor 7, and that results in the activation of factor 10. Then you also have the intrinsic pathway, which is so named because all the components that are required for its initiation and progression are present within the blood itself. And it involves the activation of factor 12, which is also known as a Hageman factor, by contact with negatively charged surfaces, such as exposed collagen at the site of injury. And when factor 12, or Hageman factor, gets activated, then it activates factor 11, which in turn activates factor 9. And activated factor 9 forms a complex with its cofactor, factor 8, or factor 8A is the activated form, on the phospholipid surface. And that complex, along with calcium ions, is called the tenase complex, or intrinsic tenase. And that complex plays an important role in amplifying the process of clotting by cleaving and thereby activating factor 10, right? So both the intrinsic and the extrinsic pathway are means by which factor 10 may be activated. And then that will in turn go on to ultimately result in thrombin cleaving fibrinogen to form fibrin, and that serving to reinforce the platelet plug.
Wow. Well, as Jonathan comes up for air there with that awesome description, listeners, you can see that there's lots of factors involved, lots of components. Jonathan, this is such a tightly integrated system. Is this what Behe meant by irreducibly complex? Can you flesh out what he meant in his 1996 book when he said that this system was irreducibly complex?
Yeah, so this exhibits irreducible complexity all the way down, right? So, for example, it's not enough just to have the mechanism for achieving the clot of blood. You also have to have a mechanism for preventing excessive clotting, because there's literally enough prothrombin in 1 milliliter of plasma to clot all the fibrinogen in the whole body if the prothrombin were all converted to thrombin, right? So this is the problem. You have to very carefully regulate this cascade. And so to prevent excess clotting and make sure that the clotting cascade remains localized to the site of injury, there are various regulatory mechanisms. So, for example, antithrombin 3 is a natural coagulant that inhibits thrombin activity, and it also inhibits several other coagulation factors. There's various other proteins that are involved in inhibiting the blood clotting cascade to prevent excessive clotting. And so you have to have a mechanism in hand for inhibiting the blood clotting cascade. Otherwise, it's actually going to be a severe disadvantage to have the blood clotting pathway. And this is something that typically gets overlooked when people attempt to give an evolutionary account of the blood clotting cascade. So that's, I think, part of what makes this an enigma for an evolutionary account of things. Now, in terms of the irreducible complex core, I mentioned that Behe in his book argued that at minimum, the common pathway is irreducibly complex, and that would include fibrinogen, prothrombin, factor 10, factor 5, and then you also have to have, of course, some mechanism to activate factor 10 in response to tissue damage. So what would happen if any of those components were missing? Well, if you didn't have fibrinogen, and this is actually a known condition called afibrinogenemia, the mesh-like network that stabilizes the blood clot isn't going to form. In the absence, if you don't have prothrombin, then the result is a condition known as hypoprothrombinemia, which is a bleeding disorder. And since no thrombin is produced, then fibrinogen is not converted to fibrin, and thus the system fails again to form the mesh-like network that's necessary for the formation of a stable clot. If you don't have factor V, this is a disease known as Oren's disease, then the production of thrombin is significantly reduced, and it has the same result. If you don't have factor 10, this is known as a Stewart-Prower disease, and the production of thrombin is impaired, which again prevents the formation of a stable clot, right? So if any of these components is missing, then you don't have the formation of the clot. And then, of course, you've also got to account for the origins of the regulators that prevent excessive clot formation. So the blood clotting cascade exhibits irreducible complexity in spades.
Yeah, it sounds like it for sure. Well, along comes Doolittle in 2009 with a paper titled Step-by-Step Evolution of Vertebrate Blood Coagulation. And he also wrote a book on the same subject in 2013, both of which you have examined as part of writing this series. What was the gist of Doolittle's claims? How did he suggest that it was an evolutionary pathway?
Yeah, so Doolittle basically argued that there are certain proteins that are found in the intrinsic pathway that are not found in lampreys and in jawless vertebrates, which represent early vertebrate lineage. And he argued that this actually undermines the argument of irreducible complexity. And so what you would predict on an evolutionary account of things is the earlier system should be simpler than the later system. And that's precisely what you find. And so evolutionary theory is confirmed. I'm simplifying here, but if you want to examine this a bit more detail, then you can check out my series at evolutionnews.org. But he, in the book, basically puts forward a 4-step pathway to give an evolutionary account of the origins of the vertebrate blood clotting cascade. And I'm quoting from the book here, but he says in the first stage, the first of his 4-step pathway, he says, the first stage existed in the last common ancestor of jawless and jawed vertebrates and was characterized by the presence of only 6 different proteins, 3 of which are vitamin K-dependent proteases. So what are the 6 proteins that are found in his first stage of his 4-step pathway? Well, these 6 proteins included tissue factor, factor 7, factor 10, factor 5, prothrombin, and fibrinogen. Now, which proteins did I say were part of the irreducible complex core of the system? And which proteins did Behe argue in Darwin's Black Box in 1996 made up the irreducible complex core of the system? Well, it was the components of the common pathway, which includes fibrinogen, thrombin, factor 10, factor 5, the very proteins that Doolittle helps himself to in the first step of his evolutionary scenario. And of course, he adds to that collection tissue factor and factor 7, which are key components of the extrinsic pathway, which are required for initiating coagulation in response to tissue damage. And Behe's hypothesis, of course, predicts that every coagulation system will contain these 4 proteins, fibrinogen, thrombin, factor 10, factor 5, or equivalents, in addition to there being some way of activating factor 10 in response to tissue damage. And this is precisely what the data show. So actually, Doolittle has scored a little bit of an own goal here and actually helps to confirm a prediction of Behe's hypothesis.
Interesting. Well, it sounds like he's taking a lot for granted as he goes along. What about time? You know, you hear a lot of Darwinists claim that they've got all the time they need through the evolutionary process. But you write that evolution depends on prohibitively long times to attain and fix multiple codependent mutations, where none of them confer a fitness benefit until all of them have arisen. So does this mean that an undirected process doesn't have unlimited time to put something like this together?
Yeah, I think that when you need multiple codependent mutations to work together in unison to achieve some higher level objective, in this case, creating a stable blood clot, I think that the time required for such innovations to arise is prohibitively difficult. Evolution doesn't perform particularly well when you need to make multiple codependent mutations. And so when you add a new protein to the blood clotting cascade, of course, you need to regulate it. Right? Otherwise, you run the risk of just locking the system on, which, of course, you don't want to do. And so you have to also have the origins of this activating enzyme in a manner that is coordinated with the origins of the proenzyme. So that is, I think, a challenge to evolutionary theory. And of course, the blood clotting cascade is incredibly delicately regulated. So one scenario that Doolittle proposes in his book, and indeed in his paper, is the scenario of rounds of gene duplication and divergence resulting in the origins of new proteins that make up the blood clotting cascade. What Doolittle fails to acknowledge or discuss in the paper or in the book is the fact that duplicating of genes is going to result in an overexpression of gene product, which will upset the delicate balance of the system and probably result in an increased tendency to have thrombosis, etc., or excessive clotting. And so gene duplications are likely to be subject to purifying selection and therefore removed over time. So that is also a problem that Doolittle fails to acknowledge in his paper and in his book.
Now, just how well has Behe's arguments about irreducible complexity held up since his book first came out 27 years ago now?
I think it's quite incredible how well Behe's arguments have withstood the test of time. Yeah, reading Darwin's Black Box, I mean, the arguments here and there need to be updated, but the substantial core of Behe's arguments, I would say for all of the irreducible complex systems that he discusses in Darwin's Black Box, they have withstood the test of time, and they're in fact even stronger now than they were when Behe wrote Darwin's Black Box. And that was one thing that really struck me when I was teaching on the blood clotting cascade this past year during my college program that I was teaching.
Okay. So is it fair to say that Doolittle has not succeeded in finding a viable evolutionary pathway?
That is what I would contend, yeah. And if listeners want to go into a little bit more detail on that, then I would definitely refer them to the 3-part series I wrote for evolutionnews.org. There's a lot there that I haven't said in this interview, but I would check out that for more fleshing out of this material.
Yeah, and we'll put links in the podcast description as well, so you can get it there, or just search Jonathan McLatchie at evolutionnews.org, search Blood Clotting Cascade, and you indeed will find this series. Well, folks, as Jonathan said, this is a flyover of the topic, believe it or not. Lots of factors involved, lots of things in place, and it is an amazing system that demands an answer that we don't think a natural process can deliver on. But there's lots more to dive into. Jonathan, where can listeners turn, besides the 3-episode series that you've got, where can they turn for more of your articles?
Sure. So my personal website is jonathanmclatchie.com. That archives a lot of my essays relating to intelligent design and evolution, as well as broader science faith issues, my articles relating to New Testament scholarship and biblical theology and that sort of thing. You can also find my other website, talkaboutdoubts.com, where we basically offer mentoring to people who have questions about science faith issues or other issues relating to doubts about faith, etc. So I would check out talkaboutdoubts.com. We have some intelligent design experts who are involved in that organization. So check that out if anyone is interested in science-faith dialogue.
Awesome. Well, Jonathan, this has been a lot of fun. And hey, we're actually face-to-face. This is not conducted remotely, folks. We are in the same room. And we're going to hear a lot more from Jonathan McLatchie in the future. Let's do this again soon, Jonathan.
Thank you.
For ID the Future, I'm Andrew McDiarmid. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.